Okay, so today we're discussing, well, the lecture topic is train test split, but I kind of retooled the lecture because train test split is one example of model validation. And so today we'll be discussing the basics of model validation and two techniques of model validation. One is called train test split, and the second is called cross validation. And so my understanding is that everyone has already been doing a bit of cross validation in your code. I mean, I've seen it in office hours, and perhaps a bit of train test split as well, if at all, in the code. Yeah. So today I found that based on feedback, the most helpful things it sounded like was going through with a PowerPoint first, going through the topics, and then today we'll have a bit more hands-on code as compared to yesterday, because yesterday was really code light for the lecture. But we'll do a quick review of modeling, because how do we evaluate models if we're not sure what models are? We'll discuss what train test or train validating and testing is, cross validation, three-way train test split, and then we'll do an implementation example in the code. That's all on the repo for the, I think this is 3.2. Yeah. So it's all on 3.2, including this deck. All right, so let's jump into it. Modeling review. Can someone tell me what a linear regression is? Same first question as yesterday.
It's when you fit a line to a set of data points.
Yeah.
The best fit, which may not be that good, but it's the best.
Yeah. Were you going to say something to add to that?
Yeah, I was going to say that the method we've learned so far is ordinary squares. We've also practiced with regularization, which adds to orders between some square errors.
Yeah. So linear regression is a modeling tactic where, as exactly as you all told me, we have a number of data points within our data set, and we want to fit a line that minimizes or best predicts or perhaps best describes the data points in front of us. The way that we determine that a line best describes the data in front of us is by making sure that line minimizes error. If we're minimizing, and remember there's two types of error to minimize. The closer our line is to those points is the more we're minimizing error due to bias. And if we had every data point in the world, we would minimize bias and not worry about variance. We'll talk about that more in a second. But nonetheless, if we get closer to the dots, we're minimizing, or the points rather, we're minimizing error due to bias. However, as we introduce new points, if we fit our model too closely, we overfit our model. It is too complex of a model and goes past our sweet spot of that magic graph that we discussed yesterday with the bias variance trade-off. Then when we introduce new data, we will have a type of error due to variance, where our model does not describe the out-of-sample data and is quite far from those out-of-sample data points because it was built on a very specific set of training data points. So imagine for a second that we have every possible data point for some system. Like imagine that we're modeling the outcomes of hockey and hockey ends. Like hockey is no more. In addition to being really sad, we would no longer have any new points added to our system. So how would that affect our modeling tactics?
Well, you want to reduce error due to bias, and most people are not worried about variance since we're not points on our model.
Exactly. Do you hear that? We're only going to reduce error due to bias because error due to variance is the result of applying out-of-sample data points. But if we simply have every single data point in the universe, like we know the Caps are going to choke in the playoffs no matter what, then we just reduce our error due to bias. Exactly. So if we have every data point ever, there's no such thing necessarily as an overfit model, because overfitting means that our model is too fit to a specific set of data points in anticipation for data points that we have not yet seen. But if hockey literally ended and we only have hockey data from the prior seasons, we would just get it as close as possible to describe the points in our set. Does that make sense? So that's not the real world. Thankfully, hockey's still active. So let's say we have that same plot, right? And we fit this line here. And now we have these new out-of-sample data points, those blue guys. Those are our new out-of-sample data points. How does that affect our modeling tactic? It's very similar to the last answer. Don't overthink it.
You want to make sure you reduce variance as much as possible. Well, not as much as possible, but you want to reduce variance to a certain extent so that your model doesn't fail to predict the new data.
Exactly. If we have new data points, then we're concerned with error due to variance just as much as we are error due to bias. And we want to find the sweet spot where our model correctly evaluates the difference between our data we already have and our potentially out-of-sample new data. So given that that's the case, and we are always going to have future out-of-sample data, pretend like we only have the red points again. We don't have the blue points yet. We're going to get those eventually. But for now, we have only these seasons, we'll say, of hockey data. Can you think of a way that we could simulate out-of-sample data points? We only have the red points. The red points are not descriptive of the entire universe of outcomes, but we want to build the best model we can. It's a tough question. Does anyone have a guess? Yeah.
Just using the train test split stuff, we would only build our model on 80% of the data set and then test it on the other 20. Pretend those are new outside value points already.
So he said, use train test split to pretend that we have some new data and old data in our current data set. What does that mean? Someone else? Yeah.
So we're just holding some of the red dots out when we're making the model, and then so we can test on the other ones.
Exactly. So if we have a system where we have all those red points, we could take out some of those red points, even though we already know what they're going to be, build it around the ones that we still have in our data set, and then add those other red points back and be like, oh, let's pretend like these red points that we did have in our data set are now out of sample points. How did we perform? That's the thesis of train test split. The thesis is we want to simulate out of sample data using data that we already have in our universe. There's a number of different ways that we can do that, and we'll talk about those number of different ways. But the important takeaway there is we can simulate out of data outcomes by simply looking at only some of our data at one time. And the key there is only looking at some of our data at one time. There's different ways in which we can look at only some of our data at one time. And those are the different types of methods that we'll delve into. So the first is the holdout method. It's a train test split method where we have a training set of data and a testing set of data. And typically we'll take 80%, which is fairly arbitrary. It's kind of just the data science norm to some degree. And we'll call that 80% of our original data our training set. So with that training set, we will build a model used to train our classifier. In other words, our line, if we're doing a linear regression. If we're doing a linear regression, the classifier is a line. There's multiple different modeling tactics, of course, so this is abstracted to say classifier. But in the context of linear regressions, this means little to no line. The testing set is used to estimate the error of our training set. So you can think about this like we had 80% of our data points, and then we did it against, or we built a model, and then we threw those other 20% and splattered them on our plot, and we looked and saw how our model performed. and then we can adjust accordingly. And we can do this process iteratively for not only selecting the model that we want to use to explain our data, but then tuning that model we've selected. So we'll talk about that more in a second, but we tune to it. So this is called the holdout method, where you use 80%, you just leave 20% to the side. So you don't touch that 20% until you test it. What are some advantages of this? It's easy to do. What else?
You can kind of see how your model performs before sending it out into the wild, I guess.
You can see how your model performs.
Before like sending it out into the world.
Yeah, you can test how your model perform or evaluate, simulate how our model is going to perform in the real world. What else? It's kind of a subset of easy to do.
Well, you can do it right away. You don't have to like wait for more data to have.
Yeah, you can do it right away. The specific thing I'm thinking about is this is computationally what we say inexpensive. It does not take a lot of computing power. And the terminology of expensive or inexpensive comes from you have to pay for computing power. So when you use Amazon Web Services, for example, you have to pay for computations you run. This is a relatively inexpensive computation to run. It's very simple. You just do a linear regression on 80% of your data once, one linear regression on 80% of your data, and then you look at that linear regression and throw in our test points and evaluate. That's pretty computationally simple. What are some disadvantages?
When you were explaining the last part, to me it seemed kind of off that you would remove some to account for the blue. Because basically what I'm thinking is the disadvantage is that like a black swan event is not really shown up in your training set. I mean, you could, but like with the visual representation from the last slide, it's clear that the red data is grouped there and the blue is out there. So how do you know that it's actually going to bring in blue as essentially?
Tremendous. So you covered the core disadvantages. The first is you're leaving out some of your data. Like that's just bad, right? If you, especially in the case of a small data set, imagine just sacrificing 20% of your data. Remember yesterday when Roland was talking about, he asked a question about how we had 8 data points and we modeled the complexity. Imagine if we did train test split on that and eliminated 20% of our points, right? So if you have a small data set, you're making it even worse and harder on yourself to produce a good model. That's one thing, one subset of what you said. The second subset of what you said is, what if there's a black swan event? That is something that we did not predict. We had no idea something like this was going to happen. And it caused our entire model to not account for some situation.
Does that mean if in one example, we take our training sets of 80% of those points and in the remaining 20% that's left out happens to be 5 major outliers that just didn't make it into that training set, and we model just on that one time, then it's going to have high error.
Yeah, so what you're getting at is how do we determine our training testing points and our testing and our training and testing points? And the answer is yes, they would be randomly selected. But even if you randomly select, there's still a non-zero chance that the black swan event is wholly in the test event. So what you're saying, yes, the outliers can wholly exist in the test event only. And that is a possibility that we would not see. We would be blind to it because it's totally in the testing set. So can anyone think of an example of like a real world data set example of I almost gave away the example, of where you could really mess up a black swan event, so to speak? Stock market.
This essentially comes down to, so this method's not going to be very accurate unless it's better the more data you have. Is that kind of correct?
Yeah, that's
otherwise it's
not very accurate. Yeah, that's generally true for almost everything. But especially true. Sorry, that was meant to be mean.
No.
But especially true when you're eliminating 20% of your data. So yeah, you rely on a lot of data, like stocks, yeah. But I'm thinking even different than stocks. Stocks are fully quantitative and like on a cumulative distribution. Think about predicting amusement park attendance. And you have a categorical variable for day of week.
Use this yesterday. No,
What, did you have an answer?
no, I just made a face because I was using, I talked about this the other day.
Oh, yeah. So,
I was excited for it.
yeah, so imagine a categorical variable for day. And let's pretend like there's obviously 7 days of the week. Let's pretend like our testing set had a number of the variables that were Saturday and Sunday, and our training set was Monday to Friday. That would result in substantial problems for our model evaluation. And even if it's random, the fact that there's only 7 categorical variables increases the propensity for this so-called black swan event to occur. That's different than, say, a wholly quantitative variable, because a wholly quantitative variable, there's usually a sliding scale in the distribution of values. It's not just like 7 strict values, which means that categorical variables exacerbate the chances that we have a so-called black swan event. Does that make sense? Yeah. Yeah, so here's exactly this summarized in our doc spec. Advantages of training test split on the holdout method. It's fast, it's simple, computationally inexpensive. Disadvantages, we're limiting some of the data, and we may have imperfect splits. We have non-random splits, and our dog really doesn't like that. Okay, so how can we use the maximum amount of our data while still ensuring model integrity? Multiple random samples. Can you explain?
Equals cross-validation will take your data and split it up a number of times into multiple random sets that don't match.
Yeah. So you're like here. We'll get there. But exactly what you said is right. And I'm just going to make it even more surface level. So in the example of the holdout method, we said 20% of our data, not even going to look at it. I'm sorry, I don't know your name.
Nicole.
What Nicole suggested is exactly right, that we could create different samples of our data and train against those different samples and test against the other samples that weren't in the training set that we just used. In effect, we're using all of our data step by step and use it in whatever parts are in our data set we train on, and the part that we omit is what we test on. And we keep iterating through that process some number of times, depending on the number of different splits we made in our data for the number of different training sets. So a visual representation really helps. We can split our data into a number of different pieces, known as folds, and we would train using k-1 folds and use a different fold for testing. So you can think about this like, in this case, where we have 4 folds in our data. We can train against these 3, and then test against this. Train against these, test against this, all the way through the possible combinations. Does that make sense? And in doing so, we're producing a number of different models, right? Because when we did experiments 1 through 3 and you omit 4, you produced one model. And then when you did 2, 3, and 4 and omit 1, you produced another model. When you did 1, 2, and 4, you omit 3, you produced another model. So on. So 4, choose 3. And we test against the final fold, right? So in producing all these different models, what cross-validation does is takes the average of where that line would be that is best for all those different possible outcomes we described, and uses that line to say that's what our model should probably be. So you can think about it like, I'll take your question in a second.
Yeah, no.
So you can think about it like, we have one line here, right? And then let's pretend like we had another set of points. Unfortunately, I can't generate another set of points, but imagine the line gets shifted vertically up. And then imagine another set of points shift the line vertically down. We would take the average of those three to say what our model would be across those three data sets. And then we'd say that's what our predicted model is. That's what's going on behind the scenes. What's your question?
Just generally speaking, sorry if this doesn't fit perfectly where you are. Do you measure variance the same way that you measure bias, just like after the introduction of the data against the model that you trained?
Yes.
Okay, cool.
Yeah, the mathematical definition that we used from yesterday shows that we evaluate the oh man. Here you go. As per the mathematical definition of evaluating variance, we take our estimated f, our error of the estimated f, subtract them, because that's our variance, and square it.
Okay, cool.
So exactly. Okay. And then the error for this is calculated as the sum of the error divided by 1 over k, the number of folds, because it's an average. This is just an average formula. Summing and dividing by the number of things we did. Sometimes an application can be scary. This is just like literally divide by the number where the numerator is the sum of the error. Average. So let me ask you this then. How many folds are in a k-folds model? No. No.
Oh, sorry.
K. So when your friend sends you that terrible text message, like K period, that's how I kind of like to think about this. Yeah, I Googled for K text for this. And then I X'd this out. It looked really, really hacky. I like that. So imagine if we had K equals 10. Let's just do a visual representation of what we would be doing. At first, round 1, we have these 10 splits, and we train on 9 of them. And then we're like, this model was omit. So we test against that validation set. See how we did. We have a line, and we have error. We get some error from that, right? So just stash that error for a second. We go to the next round, and we omit the second one. Make a line based on 1, 3 through 10. We get another error, we stash that error. And so on. The summation of those errors divided by the number of splits we made, in other words, the average error, is our error. And our model, therefore, is going to be an average line that best fits the points in our data set. Is that clear? It's like what would be happening all the way 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The yellow is just going lower, and that means we are not training on that bit of yellow, even though we just trained on that bit of yellow in the previous model. So you see how we're using all of our data, but just not at the same time.
Can you scroll 2 slides up? You first show about the folds. Yeah. Is experiment 1 to 4, is that a round 1? If you scroll down now 2 slides, is that a round 1, or is that a complete, is that 4 rounds by themselves? You see what I'm asking?
I'm not sure what you're asking.
Like a complete round testing, and then you average the models and test it.
So this is a photo of like
That is,
of going through if this were 4. If this were 4. So
It's experiments like this.
pictures are equivalent. Is that the same as 2 slides down? Or this?
yes, so in this slide, we're taking these and testing against this.
Okay, and for experiment 1 over there in the white space, are those multiple rounds, or is that what? I don't know. I'm trying to make a weird comparison.
Oh, yeah. Each row is a round.
Okay.
This is all the data. The white for that experiment, that round, is all the data we're using against the gray omits part of that data. That's one line. We stash that in. We do the same thing here, and then this is the middle gray part is the part we omit. And we stash that in, and so on and so forth. So this is each round, where experiment is 1 round. We produce 1 line per round. Does that help? What is the question remaining? Don't get too tied up in the visuals. I'm like exceptionally visual, so.
So, you take this, you take the average of the errors. Could you repeat how you get the, so you have 10 lines at the end of the 10 rounds.
Mm-hmm.
In the other slide. And how do you settle on the final fit?
The line that most resembles our average error is how we determine which line is best. So if you think about this, if we had 1 above, 1 below, and 1 in the middle, our average error is also the 1 in the middle. That's the one we would settle on. Does that help?
Yeah.
Okay. All right. So there's another type of cross-validation, which I'm going to talk about it. We won't do it in code. And yeah, it's just a separate method within scikit-learn. So I could show you the code for it, but I'd rather you just know the concept of it for now, and then not worry about implementation for now. Leave one out, cross-validation, is where we do cross-validation, but K equals the number of data points in our set. K equals N, where N is the population. So how many experiments would we do? We would do N. Well, N minus, yeah. Oh, you're cheating.
No.
Okay. No, you do N. And then the N, at the N minus 1 time, you're validating against the last one. So we do run N experiments.
Oh, they gotta include in the final test.
Including the final test. So we run against every single point in our data and leave one of those points out and make a model. And then we take another point out, put that one we just used back in and do it again. And do that again and again and again. So yeah, that's pretty straightforward.
Are there situations where that would be better than a K-folds one?
There are.
We'll
Talk about
that, I guess.
Yeah, that's exactly where we're going. Before we get there, let's talk about a high number of folds results in what? A lot of computation. Expensive. What about our model? What do you mean by better fit?
Better predicts, less error.
Less.
More bias.
There it is. It's a more biased model, because it's fitting to each of the individual points. It's taking each individual point into account to a greater degree, the more folds you do. Think about it. If you just had 2 folds, you're just averaging against all the data points once, averaging against all the other data points second time. Whereas if we have k equals n folds, we're doing every single point except one. And we're fitting to every single point. So we're probably going to have a really nicely fit line against our training set, but it's also probably potentially overfit, right? Because it's very responsive to the training data that we've included. So low number of folds results in what?
High variance.
Yeah. Well, no. High number of folds means low bias, high variance.
Oh,
So low number of folds. Yeah, low variance, high bias. You can think of like, because you're not taking into account the points to the same degree, which means that it doesn't fit each of those points just as well. So we have a lot of error due to bias. Our points are far from the line. But future out of sample data points may be better modeled by that line, because that line is not so married to our training set. Yeah.
But you can also control, even with a really high number of folds, if you're limiting the number of parameters that you're willing to use or the degree you're willing to work, then that should control the bias that you get, right? Okay, so just-
It wouldn't necessarily. So the question was, why can we not control the bias by our model selection? Right? You're saying different degrees? Different degrees would be just like a different model.
Yeah.
Because even if we did 1 degree versus 2 degree versus 3 degree, each of those models is going to fit to every single point except for one, which means it's going to reduce the bias to the best it can, regardless of the degree of the polynomial. It's going to try to fit those points the best it can, which means it's still going to produce potentially an overfit model. In other words, fitting to every single point results in a strong reduction of bias, regardless of the model you use, which is a tremendous segue into why perhaps we would even use a high number of folds or a low number of folds, or what the value is. Like maybe we would intentionally use a high number of folds, or intentionally use a low number of folds. So yeah, here's a summary of what we just discussed. Let's hammer that in real quick. So with a large number of folds, we're making our model more complex, right? And we know that more complexity drives down bias because our model best fits the points, but also drives up variance because it doesn't best predict out of sample data points. Likewise, a low number of folds does the inverse. Low complexity of our model, which means low variance, high bias. So again, we want to be somewhere in that sweet spot. So a common question is, how many folds do we want? For large data sets, there's just like typically k equals 3 is typically okay. 10 is just like a typical norm for being sure that you're not getting diminished
I've
returns.
been told it should always be 12.
She's been told it's always been 12. Truthfully, we will. Yeah. If you, I'm by no means all-knowing. For a large data set, typically when you get to 3, you're marginally reducing the error, very marginally when you increase your k. But in a future lecture, I think that I'll be doing, will produce a function that will find an ideal value of k. And you can even think about how you do that now. But nonetheless, that begs the question of why perhaps we would, going back to Caitlin's question, why perhaps we would use a very biased function like intentionally, or a very non-biased function. And this take a step back. Take a step back out of train test split. You're just given a data set. And the goal is to produce a model. At a very high level, what are the steps you need to take? Don't even think about like this specific of train test split. Like at a high level, what steps do you need to take?
Here's the model type, train it on something, test something against it.
Done. We want to choose the model type, tune that model type that we chose, and test it. So that's step 1 and 2. Choose a model type versus tune that model type. So you can think it's like step 2 is very much a subset of step 1. So returning to Caitlin's question, when we have multiple degrees of a polynomial that we could choose from, oftentimes if you choose, I'm just going to tell you this instead of trying to like yank it from you. Oftentimes, if you choose an incredibly high k, perhaps even k equals n, that will be very indicative of the model you want to use. Because you could try, think about it, you could try one model with an incredibly high k equals n, another model with an incredibly high k equals n, another model with an incredibly high k equals n, and you know that's going to be overfit. You know all those are going to be overfit. But you also know that you should get an incredibly low error among that training set based on overfitting. And so if you think about it, if you chose like a first degree polynomial versus a second degree polynomial versus a third degree polynomial, and you're trying to model this, and you really dial up for each of these, you really dial up the k equals n, whichever one produces a minimum error due to bias alone, because we're not testing it against other stuff, is likely an indicator that that's the model you would want to choose. And that's kind of the tricky thing about data science sometimes, is that's not an absolute rule. It's a heuristic for selecting a model to evaluate our data. And then another caveat to this is the only models that you all have been formally taught so far are linear regression and different iterations of multinomial regression and lasso and ridge regressions, which are all kind of in the same sort of class of making a line. There's other types of models that like eschew the logic of lines altogether. And perhaps those modeling techniques would work really well as compared to a linear or anything regression-based. Linear regression-based at the very least. And so choosing a model can sometimes be very influenced by intentionally making a high bias. And then after that, after we choose our model, we can try to tune that model and test and see if truly that should have been the model we picked, or maybe it did result in substantial overfitting, and we should go back and look at some other models. Go back to step 1 and pick in our model. Does that make sense? It's an iterative process, and there's no absolute answer. However, to get closer to the model selection, dialing up complexity should answer, like think about it, complexity is high for all of these models. Therefore, we know they're all going to be overfit. So that kind of controls for the idea that they're all going to be overfit. Now let's choose the one that truly does the best, assuming they're all under overfit conditions. It's kind of the way to think about that.
So you overfit them all and see which one works best, and then you do like k-folds instead?
So in the process of overfitting, you are doing k-folds.
But not doing the LOOCD one?
It depends. Determining which type of cross-validation we're doing kind of depends more on our data set than anything. Leave one out versus just regular k-folds versus, even holdout method. But the point here is that dialing up bias, whether you use cross-validation of leave one out, regular cross-validation, or just the holdout method, dialing up bias should be some kind of leading indicator, if you will, of the type of model we should choose.
So what you're saying, just want to paraphrase to make sure I'm getting this, is that you're coming out of these
data set, you don't know what kind of model you're going to use. So one way of going about how to pick your model is just using an intentionally high K that intentionally overfit it, and then from there, dialing up your bias, and then that should give you some kind of idea of which of these models was the best model.
Yeah, exactly. And that's by no means like a step-by-step, like that's definitely what you do every time. That's just one method that is often very helpful. I want to emphasize that. That is not a rule. That is a method that myself and others use that works very well in many cases. The rule is this expression, right? The rule is the graph of bias variance trade-off. That is the rule. What I just described is a way to apply that rule. Okay. So there's also three-way data splits. This is the last thing I want to touch on. We can, in addition to just like training and testing, we can add a validation step where we train, validate, train, validate, train, validate. And then when we finally are satisfied between those two steps, we then bring in our testing data. So think about this. You have a data set of 100 points, and at the very onset, you take 60 of them, and then 40 of them. You split that 40 into two. So now you have 60, 20, 20. You use that 60 to build a model. You train it against the first 20 set. You keep doing that back and forth with that 60, 20, 60, 20, 60, 20. Once you finally think that you've made a model selection you like, you then can test the tune that model against that data set. And then once you think, all right, I've got it, this is the model, this is going to explain everything, you then bring in that other 20% that you left out, and you test and look at it. And that's it. To make any change after that, you're going back to the beginning of the funnel. So you have like three types of data sets. You have the training set, which is a set of examples used for learning. The validation set, a set of examples used to tune the parameters of the classifier. And the testing set. Critically, once you have the final model set, you should not do any additional tuning, because then you're just cheating yourself and you're ruining all the prior validation work that you did. You're in effect being like, okay, I pretended like I was releasing this model into the wild, and then when it was on its way out of the desk, I literally grabbed it, snatched it, and put it back in. That's like the equivalent of like trying to test, or excuse me, trying to redo things after you've released your model into the wild. So it's like a full-on simulated leaving home, leaving the nest, training the wild model thing.
It's like your model is a millennial and went to college, and then you came back after college, like, yeah.
Yeah. Yeah, your millennial is like a college screw up. Screw millennials, am I right?
I gotta eat you out.
Exactly.
Get off my lawn. I'm sorry.
So the procedure in one single step or one single slide for the three pronged approach, divide into training, validation, testing. Select our architecture, which means the model type. We could use a linear regression, a random forest, decision tree modeling, k-nearest neighbors, all these things that you are going to discuss. And then tuning parameters, K. Train the model using that training set, evaluate the model, repeat that process of selecting the model, training it, looking at it, and so on, kind of like a for loop, until you're satisfied. And then select the best model out of all those different possibilities that you've tried. And you're like, all right, this is it. You're gonna release it out in the wild. You put it out in the wild, and then you test it against your final testing set, and you're like, that's it. Explains everything. So visually, it looks like this mess. You have your test set, which goes over here. Your training set, which goes right here, the blue. The validation set, which is the red. And what you do is you select multiple models, which is what these different dot arrangements with lines are. You build models around them and test them against your validation set. That's my middle school email, so enjoy. And yes, I am a soccer team. And you try that a number of times, and then whichever one produces the minimum number or amount of error, that's the model that you select. And that's your final model, and then you go and you use the data that you never used before to find your final error. And that final error is like, you take this model, you report it to your boss, you're like, hey, I found this sick model, so ill, the error is this. And you can cite that exact error because you know it from your final training set, your final testing set. And that's the value of the three-pronged approach.
This might not exactly apply, but is there any way, maybe go to slide before what you were just showing, so one more up. Is there any way you could say like where the lasso and the rich stuff we were doing in our lab fits into that?
Yeah, so that's part of the model type. That's part of the architecture step. Depending on the model type you're using.
So we're using like the lasso and the rich.
Yep. That's exactly what you're doing. Okay, so parting questions before we dive into the code. Oh yeah, I like this one. Penguin shirt, you gotta answer it. Is a twofold cross-validation the same as a 50-50 test train split? I think you're reading the answer in the comments.
No, I have a PDF of. I'm gonna say no.
Why?
I don't have a good answer. That's just what I feel like it is.
Think about it.
I really have no idea. I was gonna ask a question about this, I think. So, if you have 100 things and you're leaving out 20,
I'm getting re-quiz. Okay. Yeah.
and you leave out 20, are you leaving out like 1 to 20 and then 20 to 40 and so on, or do you leave out 1 to 20 and then 2 to 21?
So you're describing in cross-validation, which pieces are you leaving out? It's a random set of pieces every time.
Okay.
But we just visually represent it as segments.
Okay, that makes more sense.
Because that helps us visually. Because otherwise, like, how do you know what I mean?
So I'm gonna say no
Because
at the end you average all the errors and then I really have no idea on this one.
you're in the right zone. So, and that's what you get for wearing a penguin shirt. The twofold cross-validation is distinct from a 50-50 train test split. This could be worded like, what's the difference between twofold cross-validation and a 50-50 holdout method? Does that give it away? Between cross-validation and holdout?
Is it the difference between running it twice and just running it once?
Yes. Holdout method. Remember, we take 80% of our data and we don't even look at the other 20%. You don't even look at it. And the twofold cross-validation, you do use all of your data. You do multiple regressions on different parts of it and take the average. So generally speaking, the cross-validation is going to be more accurate, generally speaking. Also, if the Penguins win the Stanley Cup, I win the bracket pool, so it's like kind of bittersweet.
Well, you're going to this, so you're gonna win.
Yeah, totally not. Oh, yeah. Well, two different XY splits produce the same model score. Well, two different 50-50 splits produce the same model score. Yeah, maybe, but it's very unlikely. No. It would literally mean that you took the same random samples, one after another. So you're right, it could happen. Theoretically, it's possible, but
Is the randomness of your folds independent of each time, or is it like you take the data out that you have used to test it, and then you do it from your data set?
Great question. So is the randomness of our folds, when we take those random bits of our data, is it a new random bit every time, or is it those same segmented random bits? It is the same segmented random bits. We take k number of random samples, but then those random samples need to stay static, because otherwise we're just kind of producing noise. We need to leave out the same amount of data to test against the rest of our model. Think about it like this: when k equals n, and like the data point is the k, in that example, it would be impossible to change what our random sample is in that example, right? It always has to be that k, or that data point. The same reason that that is true is why when you have 3 data points, there are 3 random points, but it's the same 3 random points that you sub in and out.
Is that what the functionality with random seeds?
Random seeds, random states, yeah. Yeah, exactly. Random states are valuable because then you as an individual can produce the same models, but they're still random samplings. Yeah.
I have a question that's kind of in the direction of going back to the last slide when you're talking about the error from each model, and then you can go back and say, like, this is the final model, and here's what the error is.
Mm-hmm.
When you're actually measuring the error, like, is that R squared? Like, what do you mean when you say this is?
There's different measures of error.
Okay. So
There's different metrics you can use to evaluate the model. You can say this is the R squared, this is the root mean squared error, this is just squared error. But those things that describe those tactics, that the metrics about that model are static at that stage. Depending on which metric you choose, it's up to you. But metrics are static at that stage. My understanding is there's another lecture about metrics. Okay, so does everyone have the code? It's on the 3.2 lesson. Hopefully running through this should be relatively quick because we know exactly what's going on. We just need to know the syntax for it, is my hope. Anyone not have the code? Given that, I'm going to begin. So, got to import our libraries at the very beginning, right? So this line makes it so it plots in line within my IDE. I'm importing plot, which you guys have seen before. I'm making this figure size bigger with font 1010. Chill. I'm going to use NumPy. I'm going to use pandas. These are all things you've seen before, right? Like, I'm going to speed through these parts because it's not. Yes, it's important to know, of course, but it's not the focus of this lesson. Okay, so from sklearn, import datasets and linear model, because that's the model we're going to use. Datasets is a set of datasets that sklearn just comes with. And it comes with those so that you can try out different things, or perhaps in a teaching setting, everyone can use the same dataset easily. So that's why you've seen the recurring same Boston housing data. It's one of the pre-packaged data sets that just comes with sklearn, which is neat. So we're going to import cross-validation and import train test split. Bless you. Train test split. I'm going to declare column names, just a list called columns, where obviously the syntax of this is equivalent to saying and so on, right? But this is just more expedient. So I'm going to declare those column names. I'm going to load a data frame called diabetes from the data sets. So that's just one of the data sets that comes in sklearn. That's where that came from. and they name a data frame BF, and it's going to be the diabetes data, and the columns are going to be imported as the variable columns. And remember, we just declared the variable columns as a list of strings, where those strings are age, sex, BMI, MAP, TC, LDL, HDL, and so on. Cool. I'm going to declare a target variable within the diabetes data set, which already has something called target. That's where that comes from. This is saying diabetes dot, so it's going to expect the name of a column here, the name of a data set prep for it. So let's just look at our data set real quick. Looks good. Okay. So that stuff should be relatively painless. Now let's do train test split. I'm going to declare a variable called xtrain, xtest, ytrain, ytest, and they're going to be equal to the train test split call, which we imported from scikit-learn, which already has the pre-packaged way for making it so that we have an easy way to do train test and split. We could do this by hand, right? We could say, man, take a random sample. Random sample is equal to 80% of the whole data and call that some variable. Or we could just use the imported library, which automatically does that using the data frame. So we do that. All right, here's our first interactive question here. We're going to print the shape of xtrain and ytrain, and the shape of xtest and ytest. What is important about these shapes?
They have the same number.
Yeah, they should be the same dimensions, the same number of features. Otherwise, it will not work. So exactly, we have 88 by 10 and 88. So each of them are going to match to a value, as you just said. 354, 354, all as well. Right? Some people are confused why that's the case. If you think that if you had values that were matching against other values, imagine trying to run a regression of y against, oh, there's nothing there. It's going to throw an error. So these must be the same shape in terms of the number of values that you're using.
It's the same as testing data.
That's because we did, oh, yeah, I declared my test size as 0.8.
Okay.
Let's go back and change that. Let's make that 0.2. Great catch. Did everyone do that? Good catch. I inverted it. So we're going to fit a model. The model is going to fit at xtrain against ytrain. In other words, the model is being produced on our training testing sets only, right? And then I've gotten a lot of questions about this in office hours. Why do we keep saying predictions in our other models if we're still using the same values? Well, you were because you didn't use train test split previously. Now, you actually have something to predict. You actually have a different set of values that you're going to try to predict. So this predict line actually has value to us now. So you were Jedi mind tricked into including it previously when it was doing nothing. But now it's doing something for us. And what is it doing? It's predicting our testing set. Here's a question. Do we know what these values, y's, what the y values should be? How do you know? What do you mean it's already introduced that?
We already had.
No, we're not. We're regressing here. No, I'm being mean. I'm being mean. Keep going.
Because all this data we already had.
Yeah.
We're separating some of it. So
Yeah.
we have both the x and y coordinates. We just are assuming we're pretending like we don't.
Yeah, exactly.
Test it.
Does everyone follow that? We know the answers to what these x tests are because we separated and 20% of them fall here. But we have the 20% answers to those as well. We only trained on the other part that we only used the other part to train on that 80%. So now predictions equals the predict of that test set. So now we can make a scatter plot of y test and predictions. What is this a scatter plot of? What does that mean?
That your y test data versus your predicted y.
Yeah, where are those coming from? And why does that matter? What's coming from the model?
The predicted value.
Predicted is. Where is this coming from?
Your test.
Your test, your true.
Yeah, sure.
Yeah, exactly. Yeah, you're saying the right thing. I'm just making sure to repeat the keywords. So our x-axis is the values that they should be, and the y-axis is what our model fit it to be. So we can plot those things and label it appropriately. What is this showing us? Not great. What would great look like? Yeah. So who reads 538? Well, all of you that didn't raise your hand, now you can start reading 538. And all of you that did raise your hand, often when they do their sporting graphs and they show like exactly what a player's time versus goals should be, and then they have players that are just like way above, that's the value of this linear line. We should expect a linear relationship, and then we can see just how outrageous some individual's performance is. And yeah, I don't read the sports section that much, despite how much I talk about sports. I just read the hockey ones, which is, they've printed one hockey story this season. Okay, so now we can do the score. Is that a good score or a bad score? Not so good. Not so good.
Cheap.
What's that?
He's cheap as a week.
Yeah, yeah. Okay, everyone follow that? We just did train test split. And we got 0.4 or 0.42. Now let's try doing cross-validation. So let's import the appropriate library, which includes cross-val scores and cross-val predict. We're also going to import metrics. And we're going to do cross-validation equals to 6. What does that mean?
6 folds.
6 folds, which produces what? Yeah. I think it would do 1 minus, so 5, yeah. Or no, it would do 6. Yeah. So I created a variable to store each of those called scores, where it's storing each of the cross-validation scores for our model, which we, remember, declared up here, and the data frame, and the y, with cross-validation equals to 6. So we have 6 scores in there. So Can everyone see our scores? So we got a 0.45, a 0.61, 0.40, 0.55, 0.43, 0.57. What does that mean? Those are each error. Now we're going to declare predictions where we're going to, yeah.
So those values, is that the R squared or mean squared error or
R squared.
R squared?
Now we're going to declare predictions. Yeah.
I feel like I'm missing something. So why is cross-style score very bad to model when the model has X-ray and Y-ray in it, or does it just automatically, or does it refer to model and say, oh, you're doing LM fit, and then it fits its own X and Y and based off of the
Good question, and I should have made this more explicit. Why are we using model, where model is these guys, X train, X, Y test, and the question is, why are we not doing a new split, or why are we?
and why we both were not doing the split, because unless I misunderstand the 6-level cross-validation. What I'm wondering is if 6-level cross-validation is supposed to essentially look at every single piece of data ultimately, why is it referencing to model which has the 8% training set split in that function?
Yeah, so the question is, why are we building a model on 80% of our data? Does anyone know the answer?
Because we leave some out for the final.
Yeah, we leave some out for the final, as well as the validation, the testing. So it's not the final because we only have two sets. We don't have 3 sets. We have 2 sets, and we still need to test those cross-val scores against the true scores. So while cross-val does 6 different iterations, we still need some true scores for those cross-vals. So we did 80% cross-validations, and then we'll see the true values for how our model built on 6-fold cross-validation performed.
I just have to figure it out.
Okay.
So then when would you use the default option inside the current cross-validation to set up your test training sets? Because based on this, you're just using the test train split, where the way I've seen it implemented before is you do test trains, you do the k-fold parameter, which is going to divide your data up into the different batches, and then you loop through it, doing for each test train in that k-fold, you run through the model. Okay.
Yeah, so is your question why did we even split it at the beginning?
Why did you split it that way and not split it as a k-fold initially?
Because twofold. One is we'll do the model that you're describing in the future to find an ideal value of k. 2 is I want to hammer home the idea of, related to his question, true values versus the trained and tested split values. So what you're describing is not incorrect. What you're describing is a more, we'll get to a more efficient way. Yeah.
Okay.
Yeah.
So is this kind of running a three-way split test in a weird way? Because, so you've got your 80%, and then we're folding through that 80% 6 times, and then we're comparing it to our 20% that we held out initially.
Yes, except we're not setting aside, we're using the test data as our validations training, as our validation set. So you have a testing set, a validation set, or excuse me, a training set, a validation set, and a testing set. Test here is now our validation set. And we've not set aside some amount that is our final, once we release it into the wild, this score is the final score. So to do that, you would split it again, right? Because this, every time you do a split, it splits it into two groups. So you can take one of those groups and split that again. Which is why when I described a threefold, I said we do 60-40 and then 40 into 20-20. I used that syntax very intentionally because you split something that you already split. There's no call for a split 3 times. Or if there is, I never used it. So I guess I can't say never, but or yeah. So now we're going to predict. We're going to show the same thing that we just did for our test on the holdout method. We're going to do for our cross-validation and create predictions. We're going to calculate the R squared. Oh, what did I do? Oh. Okay. Did anyone else get the error that I got? It was because the split was incorrect. Okay, no one else got it. I just quickly diagnosed it. So we just did the same thing, same exact thing as the holdout method, but using cross-validation, which we just walked through, how cross-validation works. And then it chooses the best line. And then we're now plotting our true values versus those predicted values. And then I also printed the accuracy based on R squared below it. Or no, I didn't. There it is. So this accuracy is 0.49. Remember what the other one was? What's that? Yeah. In other words, lower. So this kind of holds up to our assumptions that using all of our data iteratively produces a better model than leaving aside some of our data and producing a model once. Is that clear? And then I left in here a guided practice as per the recommendation of GA. But it's the same thing, except it just asks you to do different splits, a 50-50 split, a 70-30 split, a 90-10 split, and comparing the test scores. So the way you would do that is you would just make your splits differently up here. And then the second part is do a cross-validation where K is equal to 5. So that'd be reappropriating this code to a T, except you're changing to 5. And the point of that exercise, by the way, is to show you different values based on different values of K, and then get you thinking in the idea of, man, there's an ideal K, I wish I could find it. And you can find it by trying a bunch of different values, which you have the power to totally do. You could brute force try a bunch of different values. In the future, we'll find a more efficient way to do that, but we don't want to show you the more efficient way until you conceptualize that you can do this a number of times to find that ideal value.
We did the cross-validation of 6, and we got 6 R squared values. At the very end, when we printed out our accuracy, R value, is that just an average of those 6?
Right, because it chooses the average model.
So you could, let's just plot the average, adding up to 6.
Yep, it's the formula that we did. It's, what is the error term equal to? The error term is equal to the sum of the errors divided by the number of splits.
Right.
So just to try to answer what you said before, are you saying that, so we have our average error when dividing by 6, and now we would pick the model whose R squared value is closest to that R squared, that like average R squared value?
Yeah. Yeah.
So we're not averaging the models, and we're just an average model. We're picking the closest model.
Oh, I see the question. you're picking the, this is doing the average model.
Okay.
This
So you
is
kinda
taking
add
the
all
average
the
model.
coefficients and then average all those, and then that's your model?
Yeah.
Okay.
Okay, so you're taking the average,
Yeah.
basically everything in that sort of model.
Question? Okay, you.
I mean, sort of, so why are we using model instead of just, the linear regression model? Why are we using models?
Model is a linear regression model.
So the model has already been, we're looking at our code. So we call model on LM fit.
Where LM is a linear regression model.
Yeah, but then it's being called on our data set.
Yeah. What's the confusion? Why would we do
I was
that?
looking at the docs for scikit, and it was, and in their samples, they're just calling it straight onto, like, this is on LM.
They're calling it
There's a model, they're using LM.
sure. Yeah, I mean,
So what's the difference between?
we're declaring that LM.fit in our case is the model.
Yeah, but is that fitting into the data that we have?
It's fitting it to the data that we told it to fit to. Yeah.
Okay. So what you call model in there is it taking some arguments?
It's using this data
Yeah.
to split. Or excuse me, not to split, to model. So it's using this.
Using our existing model that we already made.
So just leaving the X test alone, when it's splitting into 6.
X test is 80% of our data.
Yeah.
It's using that 80% of our data to make 6 folds.
Well, X train is 80% of our data.
Yes.
Okay.
Did I say X test? Yeah. Sorry.
Okay.
We're using an X train, which is 80% of our data, to produce
The model.
the model.
Okay, so if we just use LM, we use all the data.
It would depend. Well,
Yeah.
it would depend on what you define for LM. It depends on what you pass here. You can use all of the data.
I'm just interested in the people that are doing it. How we're-
Yeah. And that gets back to her question. I'm hammering home the idea of using 80% of our data to produce a model and compare it against our 20%.
Are we going back and comparing against the 20% in this code?
Yes.
Where is that at?
Right here.
Predictions part, okay.
Yep.
And that's what you pass it all of Y, and you can tell what was in model, or what was in Y but not in model.
You pass it Y,
Yeah.
and it measures that Y against predictions. It doesn't know that those came from the same model. You told it because those came from the same model when you declared this line. We know these values are from the same model, Y and predictions, because we did the split here. In other words, this line of code exists in isolation, where if you had told it that Y is 1, 2, 3, 4, it would assume that those are your Y values. But we set Y as the true Y values based on our data set.
Okay. We're just watching train back here. About Y test.
Y
Because we did all. the-
Y test. So predictions is the value of
Y test.
Y test. We're declaring predictions as the tested Ys.
Okay.
So at the end, we got all the PR squares, right?
Yeah.
And so I'm still a little hazy on, so now that you have all of your R squared, you get the average of those.
Yes.
And that's your sort of average error.
Yes.
When you're putting your model, when you're choosing your model, you base it on the mean of the R squared.
Yes.
Did we do that in here, or how do you do that?
It did it for us, which is why I walked through it conceptually, because you just wouldn't see it in the code. But that's what it's doing when it does a cross-val predict on a cross validation equaling 6.
So you might have just explained this, but so predictions, what is that exactly?
Predictions is predicting those Y values using cross-val predict equals predictions.
So that's a list of all your predicted values.
Yep. I gotta run. Go back to Foggy in 20 minutes. If you guys have other questions, there's office hours tonight at 6. How was this lesson overall?
Good. I think it's just about concepts.
Yeah. Yeah.
I feel like I have 90% of it.
Okay. Do you think the 10% was the result of instruction not being explained better or more experience?
I think part of it might be rather than having, this is just my intuition, rather than having the entirety